Yeah, it's done, sir.
Okay, excellent. Yeah, thank you. Hello, good evening, everyone. Welcome to this course and first lecture on ME5201W. This is the Computational Methods in Engineering course. My name is Kameswararao Anupindi. I'm a faculty in Mechanical Engineering department here. My office is listed here, which may or may not be of so much relevance to you, but if you come to campus, my office is room number 343 in NAC 2 building. Okay, my email is kanupindi@iitm.ac.in, and phone is, if you are calling from outside, it is 044-2257-4695. Okay, so if you have any questions or any clarifications other than what we discussed during the class, you are welcome to reach me on my email. But if there is something that you need to clarify over phone, you can kind of call me on my landline as well. I hope you are all able to see my screen and what I'm writing here.
Sir.
Yes, okay, sir. Excellent. Yes, sir. Excellent. Okay, so we have two teaching assistants for this course. Mr. Kiran Sivadas, whose email ID is me22d037@smail.iitm.ac.in. And then we have Mr. Gauri Shankar Patnaik, whose email is me22d21@smail.iitm.ac.in. So both are my current PhD scholars, and they will help us help you with the with your questions. Other than what I would clarify, if you have any additional questions, you can contact them as well. They will join. They have already joined today's lecture, and they will also join pretty much every lecture, just in case. Okay, so this course, some general information about this course is this is a 9-credit course. So we have, so we are going to meet 3 lecture hours per week. That is going to be of 50 minutes each. So today's lecture is going to be from 4:30 to 5:20, but then the lectures on Tuesday and Wednesday will be from 4 to 4:50 p.m. I'm kind of talking to my students, so because I have a course from 3 to 4 on campus, I schedule this from 4:30. But then, if possible, maybe from next week onwards, I will inform you by Wednesday or by through email. By the end of the week, we may start at 4 p.m. on all the 3 days. Okay, that is a possibility. I'm trying to explore that. I'll confirm by the end of the week through code office. Okay. Fine. So the venue is online. So we're going to meet through this link. So okay, this link is not correct. I'm going to update this with the link that we have now just joined. Okay. So coming to the learning outcomes, what are you going to learn once you do this course is you'll be able to implement solution procedures for solving linear and nonlinear algebraic equations. For solving linear and nonlinear algebraic equations, and then also ordinary differential equations, that is ODEs, and partial differential equations on a computer. So you're going to implement solution procedures, which we are going to learn the theory, and then you're going to do the programs through assignments and so on. Of course, I'm also going to give you the algorithms on which how do you code. We're going to learn all that. Then at the end of the course, the other learning outcome is you're going to acquire working knowledge of computational complexity, accuracy, stability, and errors in the solution procedure. So given an algorithm, you'll be able to say what is the computational complexity, how much memory it is going to take, how many operations it's going to do, is this particular algorithm better than another algorithm that is given to you, and so on. You also will be able to comment on, is the method going to be accurate, is it going to be stable, what kind of errors are there in the solution that you are obtaining. So all these things you'll be able to comment on for in the solution of linear equations, systems of nonlinear equations, and nonlinear equations themselves, ODEs and PDEs. Okay, so those are the broad learning outcomes. Coming to the syllabus is organized into several chapters. The first chapter is solution to linear algebraic equations, and in which we are going to learn Gaussian elimination. And then a variation of Gaussian elimination is your LU decomposition. Then we're going to discuss something about pivoting strategies. How do you pivot and then eliminate any round of errors that may cause your problem of finding a solution. Then we're going to look at operation count. How many operations are involved in a particular Gaussian elimination or LU decomposition procedure, in terms of how many multiplications are there, how many divisions are there, additions are there, and subtractions are there, and so on. So we're going to look at the operation counts. We are also going to next look at matrix inversion. what is the best way to go about this thing, and then going to look at some special cases such as tridiagonal systems and then block tridiagonal systems. Again, these will kind of evolve, or these kind of show up in engineering problems quite often, that the system is a tridiagonal system. Then we're also going to look at what are well-conditioned and ill-conditioned systems. Okay, and then finally we're going to look at what are matrix and vector norms, and then how to calculate condition number and what are its implications. Then the second chapter is solution to nonlinear algebraic equations. So once we are done with the system of linear equations, we're going to look at the nonlinear algebraic equations. And then first we're going to take one nonlinear equation itself, and then going to look at several methods, or three different methods. One is the bisection method, the other is the Newton-Raphson, and then finally the secant method. And later on, we're going to look at if you are given systems of nonlinear equations, that means multiple nonlinear equations, how we are going to solve them together. So that's what we're going to look at in the B section of this second chapter. Then once that is done, we'll move on to the basics of the finite difference method. This is finite difference method, in which we're going to look at what is discretization of spatial and time derivatives. How do we go about discretizing them using Taylor series expansion? Then we're going to look at what is truncation error, okay, and what is the order of the discretization. These two we're going to see. Then we're going to learn some kind of a classical tool which is known as a Fourier accuracy analysis, or von Neumann accuracy analysis. This we're going to learn in terms of how accurate and how stable a particular method is. Okay. Then we're going to look at the fourth chapter, which is the solution to ordinary differential equations, that is ODEs, in which essentially we're going to look at initial value problems, in which we're going to look at different methods such as explicit and implicit method, that is either Euler explicit method or Euler implicit method, then other explicit methods like Runge-Kutta methods, and then predictor corrector methods, and so on. Then we're going to look at another different class of methods known as boundary value problems, wherein information is given not only at t equal to 0, or information is given at both the ends of the problem. Then we're going to make use of a method called shooting method to obtain the solution. Similarly, we're going to apply finite difference method to a heat dissipation or a conduction problem in a pin fin. Okay. Then we're going to look at a particularly difficult set of problems that are known as stiff problems. So we'll first start off with what is stiffness. Then we are also going to look at further insights into stiffness by the application of this Euler explicit and implicit methods to a stiff problem. Then we will look at how do we overcome the stiffness and then solve such a problem. We will take an example from chemical kinetics in solving a stiff problem. So that kind of finishes the solution to ordinary differential equations. Finally, we look at the last chapter, that is solution to partial differential equations. This is PDEs, in which we will look at classification of PDEs and characteristics of a PDE. How do we classify them? Then there are different kinds of PDEs, which are known as elliptic PDEs, parabolic PDEs, and hyperbolic PDEs. So in each of them, we're going to look at what kind of physical problems are governed by these PDEs, what kind of discretization procedures are used, and what are the methods, so that's what we're going to see. Then depending on the time, we're going to look at also these two steepest descent and conjugate gradient methods, which are known as the global iterative methods. Then we'll move on to solution to parabolic partial differential equations, which are, we will look at what kind of physical problems are governed by parabolic PDEs. And then we will look at a particular method that is known as operator splitting and alternate direction implicit methods. Okay. By the way, feel free to ask me any questions as and when you have. We'll try to answer them, and and move on. Okay. So I expect you to ask me as many questions as you have as we go along this course. Okay. Coming to the suggested textbooks. Okay, there are many textbooks here. You can pick a few of them or one or two of them. The whatever we discuss in the class here would be sufficient, but nonetheless, depending on what we are looking at. For example, when we are looking at the first chapter, that is the solution to system of linear equations and nonlinear equations, you may find the introduction to numerical analysis by Kendall Atkinson to be of much useful. Similarly, there is this book by Engineering Numerical Analysis by Parviz Moin. This is also quite a good book. Then there is this book by Chene and Kincaid. This is Numerical Methods in Computing. Then there is Numerical Methods for Scientists and Engineers by Hoffman and Frankel. I think you will find some of these books to be quite useful. You can pick any of them. I'm going to share this document anyway through your portal, so you can have a look at this and then look at the books. Then coming to the prerequisites for this course, I expect you will have some knowledge of engineering mathematics from your undergrad. And from there, you already know some basics of matrix algebra. What is a matrix? How does it look like? What are some of the properties? And then some basics of ordinary differential equations and partial differential equations. We're going to look at them in a quick way when it comes to each of these chapters, but then you should have had some background. Otherwise, you can go back and maybe brush up those fundamentals so that you will kind of follow here without any problems. Then there will be assignments, which are a mix of theoretical hand calculations and programming part. So I expect that you have familiarity with one of the programming languages, such as Fortran or C, C++, or MATLAB, Octave, or in case if you are working with, you can also use Python. I prefer Fortran, C, C++, because most of the big codes that you take, which are the commercial software, they're all written in Fortran, C, C++. You know, you take either MATLAB or you take any engineering software, something like ANSYS or something like that. They're all always written in compiled languages such as C, C++, or Fortran, which are easy to learn. For example, I'm going to make use of Fortran sometimes if I want to showcase some example problems. Then, of course, you are also welcome to use MATLAB or Octave, which is a kind of an open source version of counterpart of MATLAB you can use, or you can even use Python. Although I'm not a big fan of Python because it may be slow for some of the computations, but because you're not going to do heavy duty programming, Python might still be okay for this course, but it's up to you. I will leave it open for you to learn whatever or use whatever that you know to solve assignment problems. But please mention whatever is the programming language you have used and how to you compile them and so on when you submit your assignment, so that in case we want to compile them, we would know. It may be required, we may be required to draw some graphs. So we will use some plotting software such as GNU plot. I may give some example scripts for GNU plot, which you can use. And then for programming, you can use any of the editors. I prefer to use VI or Emacs or gedit, or if you want, you can also use Visual Studio Code, VS Code, or any other editor to write your programs and compile them and so on. It will be nice if you have some familiarity with either operating with the Linux operating system, because a lot of things all these compilers are easy to install and run there because it's an open source system. Otherwise, if you have a Windows machine, you can probably install Linux as a subsystem inside your Windows or something like that. Or if you figure out how to compile your C programs or Octave or Python programs on your Windows machine itself using Visual Studio Code or something, that is also fine with me. It is not that you have to have access to a Linux or Unix operating system. Okay, so but you have to figure out a way where again the TAs can help in case if you have questions on how to use it on your Windows machine or something. We will probably come up with the document and share it with you. Okay, coming to the grading policy. So we'll have, as I said, we'll have assignments which are a mix of theory and computation. So it's about 20%. We may have one assignment for each chapter, so you can expect something like 5 to 6 assignments, okay, which will again be mix of theory and computation. The theory part is supposed to prepare you for the exams, and the computation part is your hands-on calculations in writing programs and getting results. Then there will be one midterm exam, which will be on the theory. So you'll do hand calculations, show the algorithm, write the algorithm and so on. That is going to be for 30% of the credit. And then there'll be a final exam, which will be for 50%. So together we have, 20%, 30%, and 50%. Okay. Any questions so far? Any questions so far? Any clarifications?
No, sir.
No?
Hello, sir. This is Chidambaram, and thanks for sharing that about the course, like content of this course. And
Yeah.
I just want to bring it to your attention, like there is one student, like from our batch. This is 24 batch, and he has mentioned that he has a value stream mapping meeting, means across his means other functional groups actually, and he's not driving the meeting. And the meeting is till 4:30. So this is shared by one person, sir. But I'm just bringing to your attention, if there is a I would like, means it's not a mandatory, but means if it is anything possibility that we can start the class from 4:30. That would, he has meeting till 4:30, but if he can have the class from 4:30, that would be helpful. Otherwise, like I'm just bringing it to your attention, and otherwise, like we can provide some option, like kind of a recording he can watch, and so that he can join late, or some option we can provide for him.
Sure. So this is 4:30 p.m. on what day you are saying? Is it on all days or only on Mondays?
Yeah, Arun, can you please clarify on that?
Yeah, all day it was, sir. Maybe if there is a possibility, you can consider, sir.
Okay. I think there is one more class that begins at 5, I suppose. After this class, I think, on the Tuesday and Wednesday. Anyway, I'll discuss with the code office about this and then get back to you. Okay.
Thank you, sir.
Yeah.
Just check the possibilities.
Yeah. I'll discuss with code office and then get back to you, because I think the other class is scheduled at from 5 onwards on Tuesday and Wednesday. So right now we have only class starting at 4:30 on Mondays, but then I was thinking of even preponing this to 4 to be consistent. We'll see. I mean, anyway, we'll have a recording option, but it'll be nice if we can join for part of the class, so that it's not going to be completely recording for him. We will see if there's a, yeah.
Yeah, sure, sir. Thank you, sir. And he's also checking with his company, like if he can, if he can, means what is that? Instead of 4:30, if he can leave that meeting earlier or something. But we would keep you posted in case if we get updates, sir.
Yeah. Sure. Okay. Any other questions related to syllabus or programming, anything like that? Anybody?
Hello, my name is Amit. I'm from the 24 batch.
Yeah.
So the question is, like, you have suggested that we might have to use a software like MATLAB or say Fortran, etc. So some of those softwares or languages come with a license. So in case our organizations or we don't have those licenses, how do we access those programming languages?
Sure. Yeah. So all these compilers, let us say C, C++, Fortran, they're all, including Octave, they're all free. They're all open source. So if you go for GNU software, they're all open source. You can install them either on Windows or Linux or Mac or something like that, or in all the 3 operating systems, except for MATLAB, which requires a license. This again, I'm going to check with the code office if there is a way that you can access any MATLAB licenses. That is the only one that requires license here, in case you wish to work on MATLAB. But then again, we have an alternative, that is Octave, which is completely free software. Okay. So this other one, I'm going to check with code office and get back to you if there is a way, if you are allowed to, have a MATLAB license or something.
The long-term advantage I see, sir, is that in case we want to use MATLAB for our projects and stuff, then through the subject we can build a lot of understanding and
Sure. But actually, I would say for projects and all, it will be nice if you can make use of Fortran, C++, and Python or Octave than MATLAB, because even not Octave in that sense, because see, for your these assignments, the problems are very small. You probably work with 20 by 20 size matrices or 50 by 50, something like that. But for your projects, you're going to make use of much bigger degrees of freedom, much bigger problems, which are not very efficient when you run on MATLAB. They may not be super fast in that sense. So I think in that sense, using one of these compiled languages would be probably a better thing than working on MATLAB. But again, it depends on the size of the problem. Yeah.
Understood, sir. Thank you so much.
Yeah. Thank you.
Hello, sir.
Hello. Hi.
Hello. Yeah, this is Abhijit from 24 batch. So you were telling about the time it takes and all. So do we have any general guideline for the processing thing of the computer?
No, I think the regular laptops that you have should be fine to run these things.
Okay.
Yeah, I don't think I'll give a very big problem. Maximum it might take, like when we come to probably solution of partial differential equations, if we give a 2D problem, maybe it might take 15 to 20 minutes to run, not more than that, I guess.
Okay.
Yeah.
Okay.
Everything else will run with whatever decent laptops that you have, that should be fine. You should be able to run them, compile and run them on your laptops. These are small problems. Yeah.
Right. Thank you.
Yeah. Thank you.
Hello, sir.
Yeah. Hi.
Hi, this is Vaibhav from 24 batch.
Yeah.
Are we going to discuss anything about convergence of these equations later on in the course?
Convergence, yes. Convergence we're going to discuss, yes. So, yeah, we will discuss convergence in the context of solution of PDEs.
Okay.
Okay, yeah. And as and when it is applicable to other concepts also, we will discuss that.
Sure, sir. Thank you.
Yeah. Other questions from anybody?
So just one question, sir. Does it does these like PDs and everything, like whatever the contents are showed, does it cover both the finite element and finite volume methods?
No, actually, no. So we are going to only look at only the finite difference method.
Okay, sir. Okay, sure. Yeah. Thank you.
Finite, yeah. So we are going to only look at finite difference method, primarily because this is very easy to understand and program. Okay, so that is the reason we're going to use finite difference method. Of course, again, these concepts when it comes to solution of PDEs can be solved using finite volume methods, finite element methods, but we are not going to go into those details in this particular course because that will require a lot more effort in terms of understanding coding and things like that.
Yeah, okay, sir. Yeah. Thank you.
Thank you. But you should be able to apply the same concepts to finite volume and finite element. Let's say if you're going to work with some other software which uses finite volume method, these concepts are the same. The discretization could be coming from finite volume method or finite element method, but at the end of the day, you're going to get back to the same matrix. And the question comes out to be, how do I solve this matrix? How do I solve this system of equations? So in that sense, it doesn't matter what discretization scheme we are using or what discretization method we are using.
Okay, sure, sir. Sure. Thank you, sir.
Yeah, thank you.
Sir, am I audible?
Yeah, yes.
This is Prem from 23 batch.
Yeah, hi Prem.
So just want to know whether we'll be discussing the course in terms of an application-oriented approach. The reason why I'm asking this question is this subject course as well as the content is more on a mathematical sense, right? In terms of solving equations and matrices.
Correct.
In terms of an automotive engineer, if there is some context or correlation that can be given to us to understand this with respect to an application, then it would be easier to understand the subject just from a...
Sure, definitely. So wherever possible, I'm going to give applications, connect them to the applications where they arise. Okay. It may be possible that some of the chapters, for example, solution to linear equations may not come out to be direct application as such, but I'm going to kind of talk about what are the applications for ODEs or PDEs in real life, or else even connected to some of the problems in automotive or in mechanical. Okay. What kind of problems are governed by these kind of equations. So we want to make some connections. Yeah, but primarily, but primarily the course is on more on on the computational methods which are supposed to cover a wide variety of application problems that we encounter. Yeah.
Thank you, sir. Noted.
Thank you. Any other questions, anybody?
Sir, just regarding the class video recordings, so they'll be shared with us, right?
Yeah. The video recordings will be shared through the portal.
Okay.
Yeah.
Good to know that.
So that you can go back and revise these concepts or listen to what was already taught in case if it was too fast or something. Okay. Any other questions, or shall we proceed with the lecture?
Yes, sir. We'll proceed with the lecture.
So one question, sir.
Yeah. Sure.
Attendance. How you are going to follow this attendance?
Attendance, I think office will take care of it, I suppose. From the, whoever is joining, from there we're going to take care of the attendance, I guess.
Sure, sir.
Yeah. Okay. All right. So let's get started with, yeah, go ahead.
Sir, in Mahindra, most all 10 people are joined in a single room. So,
Okay.
So only I'm joined through the link. The rest of the people are not joined. So, how we can consider for it?
Should we give the link again?
No, sir. What he was trying to say was, like 8 to 9 of us are in one conference hall here in Mahindra.
Okay.
So individually, we have not joined through, the Google Meet. So if the, the token ID is taken as an attendance, so
I see. Yeah. I think maybe we have to inform the office about that, and that should be taken care. That should be fine, I guess.
Okay,
that's
sir.
not a problem.
You can see the video. Maybe we are all sitting here.
Yeah. I think you can just give what are all the roll numbers you're attending from one room. I think that should be all right.
Sure, sir. We'll put it as a chat message every time we come here.
Yeah, that should be fine. I think office will take care of it, I suppose.
Thank you so much.
Yeah. Thank you. Okay, so let's get started. So the first chapter is on. So some of these concepts might turn out to be very new or might be fast or something. If you feel I'm going too fast or something like that, you can tell me. I'll slow down. Or if something is not clear, you let me know. I will repeat it again. Okay. So, but so that is what I would like to kind of let you know. So first chapter is on solution to system of linear equations. Okay, so where are the applications? So where do you actually get these systems of linear equations? Where do you have to need to solve these equations? Can somebody tell me where do you actually get these equations from? Any of the system of linear equations that you have to solve?
So basically, sir, when the system is of what I mean to say is first order, like vibration problem or maybe some thermal problem, or we have to predict some temperature which is probably the linear in nature. So we do this type of like what I mean to say is solution solving.
Correct. So essentially, if you need, let us say in the solution of let us say ordinary differential equations, or in the solution of partial differential equations, as you mentioned, temperature. So for example, let's say in the diffusion equation, or the heat conduction equation, we're going to end up with the problem, and then eventually that will come out to be we have to solve a system of linear equations. Okay. Similarly, in the solution of systems of nonlinear equations, also we end up with solving system of linear equations, because we have to kind of linearize these nonlinear equations, and then we have to solve the systems of linear equations. So these are all some of the applications. Of course, even if you take let us say machine learning or artificial intelligence or all these things, eventually you're going to set up a matrix, or a matrix multiplying a vector that is giving you another vector, or you have system of equations like equation 1, equation 2, and so on. So even in those scenarios, you're going to have systems of linear equations. Now we are not talking about these equations being, let's say, 3 equations and 3 unknowns and so on. We're talking about a large number of equations in a large number of unknowns. Okay, that is where we have to discuss what are the solution procedures. Okay, so in terms of either in terms of AIML or even in terms of modeling some physical problems. Okay, in modeling certain physical problems also, we're going to get these systems of linear equations. Okay, fine. So how do we go about solving them? So the most common system of linear equations is a square system. Okay, what do we mean by a square system? A square system of linear equations is something can be written like this. For example, a11x1 plus a12x2 all the way to plus a1nxn equals b1. Okay. Similarly, a21x1 plus a22x2 plus all the way to a2nxn equals bn, and so on. And then I have more equations here, and the last equation might read an1x1 plus an2x2. Second. Okay, plus and so on, plus a(n)(n)xn equals bn. So these are several equations. Let us say this is equation number 1, this is equation number 2, this
Sir,
is
I think,
equation number 2.
So I think question number 2 should be B2, right, sir?
1 second. Yeah, this should be B2. You're right. This should be B2. Okay, thank you. This is B2. Okay, so we have essentially these are the coefficients A11, A12, A1n, A21, A22, A2n. These are all the coefficients that are known. Okay, these are all known values. And the right hand side, what we have, B1, B2, Bn, all the way to Bn. These are all the right hand side values, which are also typically known. Okay, these are also known. So what is unknown here? What is unknown is your x1, x2, all the way to xn. So essentially what we have is we have n unknowns, which are x1, x2, all the way to xn. And then we have n equations to solve for these n unknowns, right? We have n equations to solve for n unknowns. Okay, that's what is the problem we are trying to do. So of course this can be again written in a matrix form. For example, I can write this as a big coefficient matrix that has a11, a12 all the way to a1n, a21, a22 all the way to a2n, and then an1, nth row, an2 all the way to ann. And then this particular matrix is multiplying a column vector, which is basically x1, x2 all the way to xn, equals on the right hand side we have b1, b2, b3 all the way to bn. Okay, so let us call this as matrix A. This is a vector x, which is a vector of unknowns, and then on the right hand side we have b. Okay, so that is basically ax equal to b, where A is the, we call this as the coefficient matrix. This is the known right hand side vector, and this is the vector of unknowns. Okay, So that is the problem. Now we have to calculate for a given A, and for a given right hand side, we need to calculate what is X. So that is the question. This is how we can solve for we can pose a problem or system of linear equations. Now, you might have learned some methods in your, let us say, college days or school days on how to solve this kind of a problem. Do you remember any of the methods there? How do we go about solving these? Do you remember any method from there? You might have solved these for a small systems, 1, 2 by 2 or 3 by 3 and things like that.
Sir, multiplying by inverse of the question matrix.
Multiplying with the inverse. Okay. Otherwise, you basically calculate inverse and then calculate what is X. That is one method. Okay.
Gaussian elimination method, sir, if I'm not wrong.
Gaussian elimination. That is what we're going to look at, Gaussian elimination. Okay. You might have also learned about Cramer's rule, maybe?
Yes.
Cramer's rule also. Okay. We'll see all these methods in some detail. Gaussian elimination is what we're going to focus on because it is very efficient and it is most convenient to work with Gaussian elimination, especially when you have big systems. Okay. So let us look at, so the idea is that now we are going to look at the Gaussian elimination method. In the solution of Gaussian elimination, as a solution of system of linear equations. Now, what is the idea of Gaussian elimination? So before we go to Gaussian elimination, I want to kind of say a few things about the matrix A. So the matrix A that we have, we call this matrix A. This matrix can be either a dense matrix or it can be a sparse matrix. What do we call as a dense matrix? So if there are, or if most of the values in the coefficient matrix, if most of the values in A are non-zero, then we call it as a dense matrix. Okay. Now, on the other hand, if most of the values or if most of the coefficients are zeros, then we call such matrix as a sparse matrix. Have you come across any of such matrices in your work or something? Are you familiar with these terms, dense matrix and sparse matrix?
No, sir.
No. Okay. So essentially, what I'm trying to say is that, let us say if I have this matrix A is, let us say, has 100 rows and 100 columns. Okay. It has 100 rows and 100 columns. That means it has, let us say, 10 to the power 4 values in it, right? There are 100 rows and 100 columns. Okay. So this is 100, this is 100. Then out of 10 power 4, if most of them are zeros, it is possible, for example, especially when you solve problems or when you look at systems that arise from the solution of partial differential equations, these are mostly lead to sparse matrices. Okay. That means you have a very big matrix, but most of them are zeros, but there are some of them are non-zeros, but these are required. You have to still find the solution to this system to find an answer. Okay. So when you try to solve a solution of PDEs, you're going to get matrices which have these characteristics that they are all sparse matrices. But for other problems, when you have a lot of global dependence and so on, you're going to probably get some dense matrices. So at the moment, I'm going to only talk about a dense matrix, and I'm going to assume that A is dense. Okay. That means most of the values in this matrix A are non-zeros. That is some value. Okay, let us say out of 10 power 4, several of them. Let us say some, let us say some 8,000 values are non-zeros, and the remaining 2,000 could be zeros or something, which we do not really worry. But then A is dense is what we assume. Okay, before we go on with by applying the Gaussian elimination method. Now, of course, there are also sparse matrices which we're going to see very soon. We will apply a special variety of Gaussian elimination for those kind of matrices. Okay, or some other method. Okay, then we are also going to say that the matrix A is not rank deficient. Okay. So what do we mean by not rank deficient? What we mean by not rank deficient is if you take Ax equal to 0, okay, instead of A times x equals b, if I want to solve Ax equal to 0, for Ax equal to 0, so the only solution to this problem is x equal to 0. Only when this vector x is 0, only when that is multiplied with these coefficients, we're going to get 0 vector here. Okay, that is the only solution. That means there is no other combination of coefficients of A or rows or columns of A that when multiplied with a non-zero x is going to give you 0. Okay, if that is the case, then we call matrix A as rank deficient. Okay, but we are not going to look at those problems, but we're going to look at matrix A to be not rank deficient. That means it has the perfect rank such that when it is not rank deficient, the only solution to x equal to 0 is x equal to 0. That is the possibility. Okay, that is the only possibility. So we assume that all the matrices that we're going to get, let us say that is coming from some physical modeling or from the solution of PDEs or from the solution of nonlinear equations or from the solution of physical problems you are trying to solve, all these are not rank deficient. If so, we have to check this that it is not rank deficient before we proceed later on. We will do that, we'll discuss that a little later. As of now, we assume that A is not rank deficient. If once we satisfy these conditions, we can go ahead with the Gaussian elimination. Okay, so we'll look at Gaussian elimination. I think this is better. Okay, so Gaussian elimination is basically a formal name that is given to this is a formal name given to a method that successively reduces the number of unknowns in the equations. Okay, what does this mean? This means that we go back. That means it's going to successfully reduce the number of unknowns in the equation. That means what we're going to do is we go back to this equation. So we have the first equation. Then the first equation, how many unknowns do we have? When I write an equation, I have a11 x1 plus a12 x2 and so on, a1 and xn equals b1. So how many unknowns I have? I have x1 to xn, right? I have n unknowns in the first equation. But we're going to modify the second equation such that in the second equation, I do not want to have dependency on x1, right? That means I want to rewrite this equation such that this equation is going to be only some factor times x2 plus and so on, some factor times xn. That means it's going to have dependency of x2 to xn except x1. That means we're going to somehow make this guy to be 0. Okay, we're going to make somehow this guy to be 0 such that we don't have dependency on x1 in the second equation. Similarly, sir, yeah.
Sir, another 2 minutes are there. We are going to join the next class.
Oh, I see. Okay, fine. I think we are started a little late. Anyway, yes, that's fine. Yeah. So I'm going to, let us say, I'm going to stop here. Anyway, we can proceed from here in tomorrow's lecture. Tomorrow, yeah, thank you for letting me know. Feel free to let me know. Otherwise, I may not, pay attention.
Okay.
Yeah. So I'm going to stop here. If you have any questions, you can ask me, or you can ask me in tomorrow's lecture as well. Okay.
Sure. Okay. Sir.
Yeah. So let's meet at 4 o'clock tomorrow. Okay. Yeah.
Yeah. Thank you, sir.
4 p.m. tomorrow. All right.
Thank you.
Thank you, guys. Thank you. Talk to you tomorrow. Thank you. Bye.
Thank you, sir.
Thank you. Bye. Yeah.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you. Hello, can you stop recording, please? Anybody from code office?
I think sir, they're not there.
Oh, I see. Okay. So how do we stop this call? How do we stop the recording? They'll take care of it later.
I think.
Okay. Anyway, I'll log out. I'll probably talk to them later. I think it's easier if they give me the permission so that I can start recording.
Yeah.
Anyway, I'll check with them tomorrow morning sometime.
Okay.
All right. Thank you, guys.
Thank you, sir.
Okay, sir.
Thank you. Bye. Yeah.